Now, having mentioned that, we need to talk about some other things. Okay, so I said equilibrium is when the forward reaction and the reverse reaction happen at the same rate. But at what point do they happen at the same rate? As in, like, is there one condition where it always has to be? Is there always going to be a certain concentration of something? The answer is no, you can change it. You can push that equilibrium where you're going to have a certain amount of reactant at the end. You can increase it or decrease it. You can change the amount of stuff. You can manipulate it. So that's what is meant by factors affecting equilibrium. You can shift how much product or reactant is left over at the end. So let's look at some of the examples here. What do I mean by that? Suppose at exactly the freezing point of water, there actually is an equilibrium where the ice absorbs energy to turn into liquid water, or water turns into ice and releases energy. So the idea is here, you can change that balance. There's going to be a certain balance of water and ice, but what if you change the system? Okay, let's think about that. Suppose you add energy. If you add energy, that's going to melt the ice, turn to water. But let's think about that a different way. That's going to help us predict what happens when you mess with the reaction. If you add something on this side of the reaction, the product side, the reaction shifts toward the product, if you add something on the reactant side, it shifts toward the product side. So we say it shifts away from whatever you added. Imagine like squeezing a balloon and the air goes toward the other part away from where you're squeezing. Likewise here, you add something here, the reaction shifts toward over here. So this is a non-chemistry, just sort of common sense example. It should make sense. If you add energy, it's going to melt the ice, turn to water because you're shifting. But let's think about that in terms of how we're going to interpret these questions. It's because when you add something on the reactant side, it shifts the reaction toward the product side, and you have more product, more water, less ice. So that's why we say the reaction shifted toward the right, and this means more of the product, aka water, less of the thing that's on the same side you added stuff to, less of the ice. Okay, this is a shift in equilibrium. The principle is called the Chatelier's principle. That's what we mean when we're talking about shifting of equilibrium. We're referring to the Chatelier's principle, the idea that the reaction shifts away from whatever you add. So look at this right here. What if you remove energy? If you remove something, the reaction shifts to whatever you remove. If we remove something from the reactant side, so the reaction shifts toward the reactant side since you remove something from there, which means less of the thing you shift away from and more of the thing you shift towards. So if you remove energy, it gets colder, which means more ice because the water froze into ice. Okay, so shifts toward whatever you removed, and since what you removed is on the left side, the reaction shifts toward the left. So that's the general summary this general summary gets at that. If you remove something, the reaction shifts toward what you remove. If you add something, the reaction shifts away from what you add. Okay, so take a moment, think about this, and then let's give this another look with an actual chemistry example. All right, so let's look at another reaction. And so suppose, okay, we've got this. It says it's at equilibrium. That means the forward and reverse reactions are in balance. They happen the same rate. Total amount of product and reactant is not changing. And then it says you take this equilibrium reaction and remove N2, the nitrogen gas. So understand that means this will no longer be in equilibrium when you remove the nitrogen. It's going to rebalance. You're going to have more of something. You're going to have less of something. What is it going to be? So take a moment. Think about that. Which direction will the reaction shift if you remove nitrogen? Hopefully you said it will shift toward the left. Remember, the reaction always shifts toward whatever you remove. So that means the reaction shifts toward the left. And what does it mean that it shifts toward the left? Okay, look at these other things. So we've already talked about nitrogen. Which one of these will you have more of? Which one you have less of? Take a moment. Hopefully you said more hydrogen, less ammonia. Okay, and of course, even though it says, wait, it says more nitrogen? I thought you said you removed nitrogen. Yes, that's true, but what you removed will be replaced by this thing shifting this way. So this stuff will turn into this stuff and make new nitrogen, replacing what you removed. Okay, that's the reason why, even though you remove this, you wind up with more. All right, look at another one. Again, consider a closed container with low reaction equilibrium. This is removed. What will happen? Okay, so take a moment. I'd like you to predict which direction will it shift. Hopefully you said toward the right. Again, shifts toward whatever you remove. Now, which reactant should there be more of at the end? Which reactant should there be less of at the end? Take your best try now. Hopefully you said there will be more, let's see, where is it? Ah, here we go. More of these things, less of these things. All right, so that's the overview of how it works with these sorts of things, of adding or removing stuff. There's really not much to add with that. So let's look at other things. Instead of adding or removing a chemical, what if we change other parts of the reaction? Look at this. Suppose a system in equilibrium is heated. How does the Chatelier's principle predict that it will respond? So remember, heating means adding energy. Now what this stands for? Kilojoules. Okay, this is a measure of energy. So when you want to solve this, you have to think, heating, what does that mean? Heating means adding energy. That means you're adding this. That means, remember, does the reaction shift toward or away from what you add? Hopefully you said it shifts away from what you add. So since we added this, it should shift away from it toward this side. So that's why I always say it shifted toward the left, and then that means more of this stuff, less of this stuff. And your balanced and the new equilibrium that will exist later on as a result of adding this energy. Okay, so shift toward the left, which means more nitrogen, more hydrogen, less ammonia. Okay, well, how about this one? Look at this. System equilibrium is cooled. Okay, how does the Chatelier's principle predict it will respond? Okay, well, if it's cooled, remember that means you're removing energy. If you're removing energy, then which way should it shift? Hopefully you said the reaction shifts toward whatever you remove, which means left. Which means, which should you have more of and which should you have less of? Hopefully you said more of this stuff and less of this stuff, as you can see there. Okay, here's another something to consider. Okay, what if you have a change in volume for a substance? So this has to do with gases. So look at the question. Gaseous component is compressed by decreasing the volume. How does the Chatelier's principle predict that it will respond? Not a gas, not a gas, is a gas. So first of all, when it comes to these questions, changing the volume only affects gases because gases are spread out. Liquids are all the particles in a liquid are in contact with each other. It's basically, it's like a solid. It's one of the compressed states. A solid is obviously a compressed state, not affected by changing the volume. Only gases are affected by changing the volume. So you look and see where the gases are on this side. So how will it respond if you decrease the volume? Decrease the volume means squeezing it into a smaller space, increasing the pressure. So when you increase the pressure, you're pushing it away from whichever side has the most gas. And this has the most gas, so you're going to push it away from this side. So it's a leftward shift away from gas, because gas needs space. It's like squeezing the balloon and you push the gas toward the part you're not squeezing. So likewise, the decreasing the volume means raising the pressure and pushing what's in the gas away from being a gaseous state, which means less of this stuff, more of this stuff. Now, what if you have multiple things that are a gas? What if you expand? Let's see, what's system equilibrium expanded by increasing the volume? Yeah, expand it by increasing the volume, which means lower pressure. So if it's high pressure, it's going to move toward whatever side has fewer moles of gas. If it's lower pressure, it's going to shift toward whatever side has more moles of gas. Now, consider this. Which side has more moles of gas? There's 5 chlorines. There's 5 chlorines. So sometimes people say, that's the same number of moles of gas, isn't it? No. That's 1 mole of gas. This is 1 mole of gas. This is 1 mole of gas. So there's 2 moles of gas here and 1 mole of gas here. So here's what happens. When you expand the volume, raising the volume lowers the pressure. It'll shift toward where there's more gas. So which side should it shift toward if it shifts toward the side with more gas? Hopefully you said the left side. Okay, there's more gas here. It'll shift toward here when the pressure goes down. And if it shifts toward the side where there's more gas, that means more of this stuff, less of this stuff. Okay, and that's the reason for these answers here. All right, try this one out then. I got a similar one. A system at equilibrium is compressed by decreasing the volume. Question to you, viewer. When you decrease the volume, will it shift toward the side with more gas, moles of gas, or will it shift toward the side with less moles of gas? Hopefully you said it, when you decrease the volume, that raises the pressure and it shifts it toward the side with less moles of gas. Which side has less moles of gas? Because it's going to shift toward the side with less moles of gas. Can you tell which one has fewer moles of gas? Some of you may have been wondering, well, 3 plus 1 is 4, 3 plus 1 is 4. Can you have a question like that where it's the same? Yeah, that's what happens. Okay, they have the same number of moles of gas, which means since neither side has less gas, neither side will be favored when you decrease the volume, which means the reaction does not shift at all. Yes, that is possible under certain circumstances. Okay, so if the reaction doesn't shift, that means the equilibrium quantity of all the chemicals does not change. Okay, so consider this one. The equilibrium is compressed, or it's compressed. How will it change? The answer is it will shift toward which side? The one with more gas or the one with less gas? Well, if it's compressed, hope you said it'll shift toward the side with less gas. But look, there's no gas. No shift. Oops, wrong button. No shift because there's no gas, which means nothing changes. Okay, so be aware that is a potential answer ticket.